Well, welcome to our lecture 3. Since we've been talking about dependability of computers, you can see that even the basic computers that we have are not dependable for whatever reason, but somehow we really need to fix this problem, I think. I mean, we have so many problems in the world, but somehow dependability tends to be the biggest issue, and that's going to be one of the things that we're going to discuss in this lecture. So what we're going to do in this lecture is, the first half of the lecture, I'm going to talk about some mysteries. We're going to finish that today in the first half of the lecture. And then in the second half, we're going to talk about labs and FPGAs. Ataberk will give the lecture. Hopefully he will not have as many computer problems as I did. He's sitting there. You will see him. But these are completely unexpected problems. One thing should, if something is working, it should continue to work and become better, right? Not become worse. And we don't know the reason at this point. And this is a very simple thing, frankly. Okay. Okay, now let's get started. This doesn't seem to work. Okay, how am I going to make it work? Okay, at least this is working. How many people attended the seminar? Okay, did you like it? Was it interesting? Some of it was probably quite technical, but I think it's good to stretch your boundaries and stretch your mind whenever you're starting, because these folks are doing something very, very interesting. We'll see if it will pan out or not. But this is to remind you that please watch it, and you get extra credit, as I mentioned, right? And this was a seminar. Sean Lee talked about the cerebral system, its advantages and disadvantages we discussed. And just to enable you to recall, these are some pictorial cues, things we've discussed. And this is your extra credit assignment. It's due March 15th. You still have plenty of time. I'd recommend doing it. You'll learn something. And again, you're not expected to give a very detailed technical summary of the talk. I'm interested in what you learned, basically, as you can see. Okay, so this brings me to general purpose versus special purpose systems. Ataberk will cover them a little bit also, but I wanted to cover them because we've discussed CPUs, right? These are general purpose systems. They can execute any program, essentially. And the Cerebras engine is an example of a special purpose system. It's an application-specific processor, let's say. Remember that it's designed for neural network training, especially. In fact, we asked them questions during the seminar. Can it execute other things? Limited capability, clearly, right? You need to be able to map the program somehow, but not you cannot map everything to this. And then there's a spectrum of things. So this is the dichotomy between general purpose and special purpose. And it's good to discuss this. General purpose computers can execute any program, easy to program and use. You can program with many, many languages, for example. On the other hand, these special purpose systems are efficient and high performance for a given program. So they cannot execute many programs. They have a limited set of programs over here, and they're difficult to program and use. In fact, we discussed that in the seminar. One of the questions I asked to Sean was, okay, you talk a lot about hardware, but what about the software? And I said that at least as much effort should go into software, and he said that actually more effort goes into software to enable this computer, right? So clearly, there's a trade-off over here. But the advantage of special purpose over general purpose is general purpose doesn't get the best performance. It gets good average performance on any program you throw at it, but it doesn't give you the best performance and efficiency on a given program that is important to you. That's why people design special purpose systems, because these things are terrible at neural network training, whereas these things are extremely efficient at neural network training, for example. But they're only efficient at neural network training, whereas these things are good at essentially everything you throw at them, for some definition of good. It's maybe good enough for your purposes, right? Does that make sense? And this is, I think, very general concept, right? We have general purpose and special purpose things in our lives. I think of computers as tools. Computers are tools that help us. Sometimes that make our lives painful also, as you can see earlier, but they're supposed to be tools that help us achieve some goals, solve problems, and have a better life, right? And you can see general purpose tools. How many of you have used an adjustable wrench like this? So you probably know what I'm talking about, right? This is general purpose. You can also have a special purpose wrench that looks like this. And it's exactly the same trade-off, right? This is flexible. It can work with any bolt or nut. It's easy to use, but it doesn't give you the best fit. If you try a nut, you may not be able to fit it best because it's adjustable like this, right? And it doesn't give you the best results or efficiency. Special purpose, on the other hand, is a perfect fit for the nut and bolt it's designed for. And so it's efficient and high performance, but usually they're difficult to use. You need to find the perfect fit first. Which wrench do you use? And it's inflexible, only for fitting bolts, right? This doesn't work for a bigger bolt or a smaller bolt. So you have to find the fit. That's why you have many, many fixed wrenches like this. So that's the same trade-off. General purpose CPUs versus special purpose application specific processors. If you really want many, many special purpose application specific processors, you have to design one for each of those applications, as you can see over here, as people have done with wrenches. You can come up with many, many other examples. I think I like this one because it's very clean. Okay, so now let's go back to what we were discussing in the last lecture, which we finished at RowHammer, but I want to talk a little bit more about that. So the goal of this discussion is I want to give you the goals of this course, basically, so that you can understand how a system works underneath the software layer and how decisions made by the hardware affect the programmer and the software in general. And also, hopefully, you'll be able to make those decisions. So hopefully, you'll be able to make a decision. I want a general purpose system or a special purpose system. This is a very easy, high level, well, easy, very important high level decisions to make, a decision to make, right? If you're a data center operator, for example, and you know you have some applications and you want to really decide what kind of hardware you should use, even though you're not going to do much with the hardware, somebody else is going to program them, you still need to make the decision. Do I want general purpose systems, special purpose systems? How do I mix and match, etc.? You really need to understand what's going on basically in the workloads, in the software, as well as the hardware that is supposed to execute them. That's why this is important, basically. It spans all aspects of the stack. So we were talking about mysteries, and remember that I told you I'm not going to talk about Meltdown and Spectre. Hopefully, we'll be able to talk about finished RowHammer and at least talk about memory refresh today. We'll see if we get to memory performance attacks. It's fascinating, but if you don't get to it, you can either watch the lectures I will point you to, or read the slides, or none of them. Basically, you're not required to do it. These are to show you that there are interesting problems to solve in computing today. Okay, people remember RowHammer, hopefully? Okay, good. I don't need to talk about that again. But basically, this is the fact that you can predictably induce bit flips in commercial memory chips. And I've already thrown you this article, for example. I find this fascinating because this is written by software people saying that forget software, it's not important. People can actually take over your system using physical problems in your computer. And you've seen pictures like this. I will not talk about this because I already talked about this in the last lecture. And you've seen that this has security implications. Basically, you can get a bit flip in memory and someone can take over your system. It could be a mobile phone, for example. Mobile phones are, of course, easier, right? Someone can sneak in a program, you can download a program, and they may actually take over your system because it's doing something. It's trying to figure out these bit flips and exploit them. And people have shown that they can do that, actually. Many, many sophisticated techniques. Or if you're running a machine learning inference that's trying to detect pedestrians, for example, in your car, by inducing bit flips in that machine that's trying to detect pedestrians in your self-driving car, you can get a terrible accuracy in your system. So what you think is not a pedestrian might be a pedestrian, right? That's what these folks show. So this is how serious these bit flips are, and we should really not ignore them. So we talked about this, and we briefly talked about how to fix the problem. I want to talk about this a little bit so that you can think about things and maybe you'll come up with some solutions, because this is a problem that needs solutions basically today. But importantly, how to find this vulnerability, how to exploit this vulnerability, how to fix this vulnerability really requires a strong understanding across the transformation layers, across the stack basically. Because RowHammer is a problem that affects, even though it's a device level problem, circuit level problem, it affects the software at the higher level. So you may actually come up with solutions at different layers. So we briefly discussed via different slides the RowHammer solutions that need to be provided, right? If your chips are vulnerable in the field, you have to solve this problem somehow, right? How do you protect the vulnerable DRAM chips in the field? There are limited possibilities here. So what people have done is to increase the refresh rate. We're going to talk about memory refresh in the next part of this lecture. But memory needs to be refreshed periodically. If you increase that refresh rate, you reduce the probability of a bit flip because you refresh the memory contents more frequently, right? So RowHammer cannot happen as easily as before. So for example, Apple, I don't have the picture over here, but Apple introduced a solution that increases the refresh rate. And they were nice enough to reference that led to their solution in the end. clearly this is not a good solution, right? You don't want to keep refreshing your memory. We'll talk about what goes into refreshing memory in the next part of this lecture. But you don't want to expend energy to keep the contents alive, because every refresh expends energy. Every refresh leads to performance loss. So you have limited possibilities because you cannot change the hardware in the field, at least today. The hardware is fixed. It's not configurable. You can configure it in a very limited manner by changing the refresh rate, for example. Okay, but longer term, how do you protect the future chips that will have these issues is actually very, very interesting. There are many wider range of protection mechanisms, which I'm not going to go into details. You can think about it. Actually, after the lecture last time, one of your colleagues mentioned one of the potential solutions. If you're hammering this row and there are rows around it, and the rows around it gets, let's say, disturbed, affected, why not just not allocate stuff into those rows that are vulnerable? Basically, isolate the rows a little bit from each other so that you don't allocate things as densely in memory. And this is a solution that was proposed, actually. This is a software solution that can be employed also. But the difficulty is it wastes a lot of memory. So there are always trade-offs between solutions. And I mean, we already discussed, well, we didn't discuss that much, but I think we already discussed actually one of the solutions that we have proposed were employed in Intel chips. But current solutions are not actually employed in the best ways, let's say. Okay, so this is just to give you an idea. So the bit flips are happening at the device level, right? The device, the memory bits are flipping, they're changing. You stored 1, you get a 0 later. And this is clearly bad, right? And this affects everything over here that you do. You cannot really trust your hardware anymore. Even if you store 1, you cannot say, oh, the data that I'm going to get after storing a value of 1 is not 1 anymore, right? So you cannot trust anything downstream. So how do you fix the problem? So this problem needs to be fixed. It's not just a security problem, it's also a reliability problem, right? So this is a busy slide where this is to show you that people are actually thinking about a lot of solutions to this problem. How do you actually, for example, design more robust DRAM chips? Can you use error correcting codes to solve the problem? We mentioned this briefly. Add some redundancy to your data such that if a bit flips, you'll detect it somehow. Remember, we talked about hamming, right? Hamming distance. You can use the concept of hamming distance, for example, to build error correcting codes. You can increase the refresh rate, for example, as we discussed. You can put physical isolation. I mentioned this. You may have an aggressor row. You can think of every aggressor row as an aggressor row, every row as an aggressor row, and always isolate. Put some distance between rows that you allocate in memory. And this way you can actually reduce the vulnerability, but there are problems with it because you waste a lot of memory, for example. You can reactively refresh. This is the solution that we propose that's employed. You don't need to know the details of it, but you can think about it. This is just to lure you into topics similar to this, for example. Or you can reduce the access rate to memory. Basically, you can say, oh, if you can somehow detect somebody is doing RowHammer, basically. You keep attacking. You keep hammering a row. And something in the system, memory controller or software, detects this and says, oh, stop. I'm not going to let you access memory this fast anymore because you may be destroying some data, right? So this sort of detection and this is called throttling. You throttle the workload that's really inducing a lot of memory accesses. This sort of throttling can be actually very useful as well. Any thoughts? Anybody? Maybe you have a different kinds of solution. These are the general solution approaches. I went through this really fast. Again, you don't need to understand everything because we're just beginning the course. You may actually understand this a lot more at the end of the course, but this is important because we're going to come back to RowHammer when we cover virtual memory. Anybody? Thoughts? Solutions? Yes, please. Mm-hmm. Uh-huh. So that's a great question. Basically, you know more than maybe some of your colleagues. Don't worry about that. DRAM is a technology that stores capacitors. Capacitor has charge, and that capacitor leaks charge. That's why it needs to be refreshed. You're going to see this at the next part of the lecture. If you replace that capacitor with something not leaking, for example, that doesn't lose its value, can that get rid of the problem? And that's a good question, basically. Can some other memory technology? Because getting rid of a capacitor in DRAM is essentially building another memory technology. And other memory technologies exist. Some of them are called resistive memory technologies. They don't have capacitors, for example. They don't have as much leakage, so you're right. But this problem is not just due to leakage also. So this problem was shown, at least theoretically, to also happen in some other memory technologies because cells are too close to each other and they affect their operation. But it may mitigate some of the problem, yes. So that's a very good, I like that you contributed because this is a different way of thinking, right? You need to maybe think about the problem differently. Can I actually move to another technology that doesn't have potential downsides? Can it fix the problem? And maybe, we don't know that technology fully yet today though. Yes, there's one more. Okay, that's a difficult one. Cancels itself up. I don't know how to do that. It's difficult. You can isolate the wires better from each other, getting rid of the interference. It's similar to this, let's say, isolation row solution, right, at the software level. You can do it at the hardware level also. But again, you lose. That's the downside. Yes? Okay, that's great. Maybe you should talk to a guy over there who looks at the relationship of voltage and RowHammer. Potentially, that could be a solution, but that's not a problem with just voltages. IEDM actually operates at relatively low voltages compared to, for example, flash memory. And the issue is maybe if you go to extremely low voltages, you can eliminate this, but we don't know how to do that yet at this point. But any memory technology that we develop, whether it's operating at high voltage or low voltage in today's range of voltages, has this sort of problem. It's called read disturb in general, and flash memory also has this problem, except it's not as bad in flash memory because you already have intelligent controllers that can solve this in your SSDs. Okay, very good. One more, I'll take last one. Yes, please. Uh-huh. Mm-hmm. Yeah. Basically, you copy the data somewhere else, right? And then it doesn't have that problem. Yeah, I see. Yeah, I mean, that's a solution that has been proposed also by folks. Of course, it has overheads of copying the data, right? So if you need to do this copying very frequently, it becomes a big performance overhead. But yeah, it makes sense. Okay, there's. I'll give you. Maybe you go because you've already talked. Excellent. So that's along the lines of error correcting codes, basically. Can you somehow use a hash function? You could do that, but again, all of these come at cost as well, because you need to evaluate the hash function. You need to see whether it changed. You need to figure out how often you need to do that. So that's a possibility. Error correcting codes operate along those lines, let's say. Okay, I'll take one last one, and then we should move on probably. Yeah. Yeah. So I think that's similar to the solution that your colleague in the back proposed. I see, without detecting. Yeah, but again, it's yeah, I see what you mean. You keep moving the data around so that you're not vulnerable, let's say. The downside is, again, moving the data around is very expensive. Yeah. Because in order to move the data around, you really need to copy an entire row, which is 8 kilobytes, and then write it somewhere. And then when you write it somewhere, what happens to the data that you wrote, right? You have that problem also. You may start swapping, but yeah, it becomes very heavy in terms of overheads. Now, people propose moving data around inside the DRAM chip much more efficiently. Like, we have some work on that without going through the memory control. That can reduce the problem. But again, you're still moving the data around. And moving data around is, in general, one of the most costly things that we do in our systems today. But it's great. I think you guys have proposed a lot of solutions. And this is tricky because every solution has to be evaluated in terms of cost, power, performance, and complexity. And there's no perfect solution to this problem, basically. Okay, so it's great that we had this discussion. If you're really interested, you can certainly look at our first detailed study, our source code, and then Google improved our source code to make it better. And later, other people improved that source code to make it even better, basically. So this was our paper that introduced the problem 8 years ago. The problem is still not solved, as I will show you. I mean, there are good solutions out in the field, but remember, it's always cost, power, performance, complexity. Where are you in that spectrum, right? And if you really want to understand, like, across the stack, this is a retrospective paper that we were invited to write a couple of years ago with my PhD student, and you can read that as well if you're interested. But the major takeaway here is breaking the abstraction layers between components and transformation hierarchy levels, and knowing what's going on underneath enables you to understand and solve problems. Basically, if we cannot easily understand RowHammer if you don't know what's happening, and we cannot easily solve it if you don't know how to solve it. You can see that there are a lot of solution directions. But the trade-off analysis requires actually a lot more understanding. So this should be 2020 and 2021, let's say. A lot of things, other things have happened. I'm not going to talk about this more, but RowHammer is getting much worse, meaning as the technology scales, as the size of the memory cell scales become smaller and they become closer to each other, this problem is actually becoming much, much worse today. So in this paper, we showed that you can cause these bit flips very easily after only 4,800 hammerings. That's very small, actually. Okay. Industry has proposed some solutions. So some folks actually, very interesting, some major manufacturers, major DRAM manufacturers said, we manufacture DRAM chips and they're RowHammer free. They basically said this. And they advertise their chips that way. We questioned that assumption. We basically said, are they really RowHammer free? Let's test it. And we basically showed that they're not RowHammer free. You can basically circumvent the protections that they put in their chips that they claim to be completely secure. We basically show that they're not secure. You can actually easily, relatively easily circumvent it if you know what you're doing. And people who really want to get to someone else's data, they know what they're doing, basically. There are a lot of smart people in the world. So what the mistake of the industry has been is they basically claim this is RowHammer free without trying to make it fully secure. So if you have a security problem, you have to prove that it's secure. You have to prove that your solution is secure. And they didn't do that, basically. They just said, oh, okay, we did something. We solved the problem without any proof. If you prove it, and if you do it in a nice way, then maybe no one can circumvent it. But they didn't do that. As a result, it doesn't work. So it's very difficult to guarantee RowHammer free chips. These are some of the results from very recent years. As you can see, this was the work that you did together with Microsoft. It's very difficult to, you have a chip, you get a chip. It's very difficult to say whether it's RowHammer free or not, because we don't know how to test it good enough, basically. And then actually, there are many dimensions to RowHammer. It's affected by temperature, for example. It's affected by different access patterns that make it worse or better. I'm going to leave it at that. And industry adapted solutions are actually very, very poor. So in this paper, we showed that industry adapted solutions can be almost completely reverse engineered. So industry says we solved the problem, but you can completely reverse engineer it and actually make it much worse. And this is what we did actually in this work with FPGA boards that you will see in the next part of this lecture. We basically showed that all of the modules that we test are vulnerable because we developed a detailed understanding of how the underlying hardware tries to protect against RowHammer. And essentially, almost 100% of the rows experienced at least one RowHammer bit flip. So you can cause these bit flips in the entire memory. And error correcting codes don't work, basically, at least the ones that are employed in industry today. Okay, and there are solutions that we propose that I'm not going to go into, but this is one solution that we proved the security of. But again, it has, even though it's fully secure, it comes with complexity cost. And you could argue that we have to pay that cost to actually be secure. And I agree with that, actually. You have to pay the cost to be secure. If you say, oh, I don't want to pay the cost, then you're not going to be secure, right? So this is a choice that people need to make going forward. You really need to pay the cost to be secure. But the takeaway is, if you have an intelligent control that detects these access patterns, you can solve the problem. But that intelligent controller comes at a cost. Okay, so you can find more detailed lectures on RowHammer, and we actually give lectures. This is a very compact lecture that talks about RowHammer if you're interested. Maybe I'll give you examples from the human life also. I guess some people know who this person is, Abraham Maslow. He's a famous American psychologist. He basically dedicated his life to understanding why human beings do the things they do. Human motivation, something we should really understand a lot better these days. But basically, he's very famous for this hierarchy of needs, right? If you look at this, he basically says you have to have your lower level needs like physiological and safety needs satisfied before you can think about highest forms of abstract art, for example. Right? That's my analogy over here. That's why everything depends on reliability, safety, and security. You have to first start with that. And I think this is true in computing as well, right? If you don't have a computer that's dependable, that's reliable, safe, and secure, or in other words, robust, then maybe you're not going to be able to do anything with that computer going forward. You have a lot of security holes, right? Or someone will take over and you will not be able to own that computer anymore, potentially. I liken this to infrastructure that we have in the world. This is a bridge. How many people know where this bridge is? This gives some side channel over here. It's a Tacoma Narrows Bridge close to Seattle. It doesn't exist anymore because this is what happened to it, a bit flip. And this is a very famously studied bridge, actually. Basically, you have this critical infrastructure. Human beings have been building bridges for thousands of years. And this is, we consider that as critical infrastructure for thousands of years. But I would argue that it's not as important. Yes, this is a safety, security, and reliability problem. But these things are everywhere. Bridges are not everywhere, right? So these things are today the real infrastructure going into the future. Of course, we should protect these as well, but it doesn't make sense to not protect these. So that's the idea over here. So I will ask you this question also. These folks are constructing a city. How safe are they? Well, depends on the bit flips they have on that road, right? If you have bit flips on that road, they may not be very happy in a second, right? So it's good to think about security and safety, about preventing unforeseen consequences. It's not about preventing what you know. Okay, these are things that I know may happen. Let me prevent that. Yes, you should definitely prevent that. But you should go beyond. What can you not foresee? How can you design a system that's robust in the presence of what you don't know? Yes, this is speculative right now, but this is really important going into the future because these systems will live for decades. That's why I think this quote over here is very important, I think. Okay, that's the question basically. Can we really depend on computers? And if you want to depend on your computer like this person, Mr. Bean depends on his self-driving car, maybe they need to be much more robust going into the future, right? Because as I said, this car will be employing these algorithms that we keep, as you have seen in the last seminar, Sean Lee, that we keep trying to perfect. But if you have bit flips, those algorithms are useless, right? That's the idea. That's the takeaway over here. If someone basically can induce bit flips in your computer, or if these bit flips happen because of some reliability concerns like RowHammer or some other reliability concerns, your algorithms may be useless. And this should be taken seriously. Okay, so two other goals of this course is really to enable you to think critically. The reason I'm giving you these examples is not because I expect you to understand everything in the examples. At least you should get the gist of it, and you should really start thinking critically, right? Okay, I've designed the greatest algorithm, but what is the weakest link? Maybe your weakest link is in the hardware down there that's executing the algorithm, right? If you don't solve that weakest link, it doesn't matter what you do at the algorithm level. Or maybe you should design algorithms that are tolerant to what's going on in the hardware. The hardware throws you bad bits. Well, you design the algorithm, it still works with bad bits. It's a tough task, but it will prevent you, it will enable you to be much more robust. So that's the critical thinking, basically. What are you missing? It's not like what you know. It's really what you don't know, or what's the weakest link that really limits you in design. Okay, and also hopefully enable you to think broadly about systems and everything in general. Okay, so let me give you some retrospective about RowHammer. So this is very interesting because these bit flips, you can call them simple bit flips, who cares, right? But it enabled a new mindset that enabled a renewed interest in hardware security attack research. So real memory chips are vulnerable in a simple and widespread manner, and this causes real security problems. And there's a connection between hardware reliability and security. It's now a mainstream discourse. So many new RowHammer attacks are being developed, actually. You can find tens of them. More to come, I think, because this is getting worse. And many new solutions are being developed also. In fact, latest is going to be presented tomorrow in a major conference that's happening in Lausanne right now. You can take a look at it if you're interested. But we should probably have principled solutions to fix this problem. And there are more solutions to come. Okay, basically, the key takeaway is general purpose hardware is fallible. It's in a widespread manner, and its problems are exploitable. And this mindset has enabled many system security researchers to look into other issues. Or what else is problematic in hardware? Can we actually find those problems and exploit them and fix them? That's the idea. And to be able to do that, you really need to understand the hardware's inner workings and vulnerabilities, because everybody is vulnerable to this problem. You cannot basically, everybody using computers is at some level vulnerable. And two of the groups that discovered Meltdown Inspector. We're not going to talk about Meltdown Inspector. How many people know about Meltdown Inspector? Okay, I think that's a good fraction. It used to be more in 2018 when it was actually widely publicized. But these are actually common vulnerabilities in Intel, AMD, ARM chips, for example, that enable you to leak information. You can get private data that you don't have access to, basically. And those were discovered by people who worked on RowHammer before. So you can see the impact of thinking in a way that says, oh, this is vulnerable. There's a lot of issues in there. Can we actually find and fix them? And there's more to come, I believe. There's a lot more we're going to discover going into the future in this sort of issues. Okay, I'll recommend you the survey that we wrote and this lecture and move to the third mystery. So given that we don't have a lot of time, I'll finish DRAM refresh. I'm not going to talk about memory performance attacks, but I will, let's see, yeah. Any questions on RowHammer? Is it fascinating? How many people find it fascinating? Okay, some people love it. That's great. How many people find it boring? It's fine to take, yeah, okay, not that many, or people are afraid, fine. Yes, there was a question over here, yes. Oh, yeah, it needs to be basically, you need to go back to 2008, around 2008. Basically, you need to go back 14 years ago, which is not good, right? Yes, one more. Yeah, that's a good question, basically. And people are trying to fix it generally, in general. Of course, at an application level, you may try to fix it, but if you're running with multiple applications in a system, you're still vulnerable, right? In an application level, you may employ fault-tolerant algorithms, for example, that can tolerate some of these errors. But you need to know what you're doing. Does that make sense? Yeah. If you want to look at the application level, fault algorithms are the ones to really explore. Very good question, though. Okay, one more. I'll take that one. I see. At the applications, yes, you can do that. But then within an application, you may still get these issues. And that requires significant changes to systems today. Systems today actually try to use memory most efficiently and compactly. If you try to isolate applications, then you need to allocate the applications memory separately from each other. But I like your thinking. So I can get rid of the problem across the applications. Okay, very good. So I'd encourage you guys to think more about this, actually. This is, I think, maybe you can find a solution to the problem, right, that nobody has thought of. As I said in earlier lectures, don't think that you don't have the capability to come up with solutions. I think with critical thinking, with different thinking, and with a lot of hard work after that, of course, you can demonstrate better solutions. Okay, let's go into DRAM refresh, because this is related to RowHammer, and I think it follows nicely. This is an old system. This is AMD Barcelona in 2006 or so. You can see that it has a CPU chip and a DRAM chip, well, DRAM module in this case. Yeah. So if you look at systems today, actually, especially high-end systems, about 50% of the cost and 50% of the power is spent on the memory, DRAM. And one of the reasons is because of DRAM refresh. We're going to talk about that. So if you go focus into DRAM, it consists of these cells. And these cells are essentially a capacitor, as one of your colleagues mentioned, and an access transistor. And data is stored in terms of the charge status of the capacitor. And basically, DRAM chip consists of tens of thousands of rows of such cells. Remember the rows that we saw? We have tens of thousands of rows of these things. And each of them stores a bit. If the capacitor is charged, you get a one state, for example. If the capacitor is discharged, you get a zero state. We will see this later on also. So unfortunately, this capacitor is leaking. And DRAM capacitor charge leaks over time. And the memory controller needs to refresh each row periodically to restore the charge. This is done in every system. So right now, for example, my phone is refreshing its memory. It's not doing anything else but refreshing its memory. So it's wasting power. Typically, you need to activate each row every n milliseconds. And today, n is typically 64 milliseconds or 32 milliseconds. At high temperatures, because leakage increases, you need to refresh even more frequently. So there are many downsides of refresh: energy consumption, performance degradation, quality of service or predictability impact. And refresh rate actually limits how big of memories you can build. So clearly, each refresh consumes energy. And whenever you're doing refresh, you cannot access memory. Right? This is a performance problem. This is also a predictability problem, because if you're doing a lot of refreshes and the program cannot access memory, it will be delayed, right? You may actually be annoyed because you're trying to do something and the memory is refreshing. So here's some data. Well, before the data, let me give you an analysis of the problem, basically. I'm not going to do the calculations, but I'm going to pose the problem. So imagine a system with 1 exabyte DRAM. Today we have that actually, almost, in supercomputers, 2 to the 60 bytes. Assume a row size of 8 kilobytes, 2 to the 13 bytes. How many rows are there? That's an easy question. You divide 2 to the 60 by 2 to the 13. So you get 2 to the 47 rows, right? That's a lot. How many refreshes happen in 64 milliseconds? 2 to the 47, basically, because every row needs to be refreshed every 64 milliseconds. What is the total power consumption? Well, I don't know. I have to calculate this one. You need to multiply the number of refreshes with the amount of power consumed for each refresh. And then what is the total energy consumption of DRAM refresh during 1 day? Then you need to multiply that power with the amount of time, seconds, in 1 day, for example. So that's a good exercise and optional homework. If you get a brownie points from me if you do it, feel free to send me email, send Digital Technique email list email. Then you will see that this is on the order of at least kilowatts. It's a lot, basically. Okay, so if you look at memory devices, as memory devices become denser, this refresh becomes a bigger problem. So with a 64 gigabit, you don't need to know exact numbers, but today we have devices that are as big as 16 gigabit chips. If they become denser, refresh becomes a bigger problem because you have many rows, more rows, and you need to refresh them. And the capacitors are even leakier because cells are smaller. So you spend almost 50% of your time refreshing. So basically, you can think of it as 50% of the time, you cannot access memory. Similarly, 50% of the memory energy is spent refreshing. So this is a big scalability problem into the future. As cells become smaller, and as more cells are there, you need to refresh more. Okay, then the question becomes, how do we solve the problem? And this is where I would like to spend some time, basically. The observation is that all DRAM rows today are being refreshed, right? The critical thinking is asking this question, basically. Do we have to do this? And this is probably a good question to ask. Not many people have done this critical thinking, but we should do this sort of critical thinking whenever we see something like this. And maybe if you know what's going on, you can actually answer this question positively, meaning saying that, no, we don't need to refresh. And that's the idea over here. So, okay, let me give you one example of the critical thinking. If you look at the retention time profile of DRAM, it looks like this. So this is all of your cells. And this is how much they can retain data for. So most of the DRAM can retain data for more than 256 milliseconds. Only a fraction of the cells have to be refreshed every 64 milliseconds. So this is the distribution, basically. This is what the distribution looks like. An overwhelming majority of rows do not need to be refreshed every 64 milliseconds. But today, we're refreshing everything every 64 milliseconds. This is a physical phenomenon. Why do we have such a profile? Because manufacturing is not perfect, basically. You have all these cells, tens of thousands of rows. Not all cells are exactly the same. Some of them are much leakier than others, and some of them are much stronger than others. And this is called manufacturing process variation. This happens in every manufacturing. If you manufacture cell phones, not everything is exactly the same. There are some differences between them. If you manufacture cars, there are some differences, basically. It's not perfect. Manufacturing is not perfect. Especially manufacturing at nanoscale levels is not perfect. When you're putting a capacitor that's on the order of nanometers, like less than 10 nanometers, then you actually get a lot of variation like this. So that's why you have this profile that I showed you earlier. Make sense? Okay. So now I've given you, maybe you can take advantage of this profile, right? Assume you know the retention time of each row exactly. What can you do with this information? Who do you expose this information to? How much information do you expose? First of all, how do you gather this information? Is another question, actually. I didn't ask that. How much information do you expose? Do you expose the retention of every single row to the software, for example? Clearly, this information exposure affects a lot of overhead. I'll take 5 more minutes, and then we will take a 10-minute break, and then Ataberk will continue. Clearly, you can see that this information is a lot, actually, because we're talking about billions of cells. It could be more in future generations. So how do you determine this profile information, and also who determines is another question. So this is an across the stack problem also. So devices have this manufacturing variation, Can you expose it to the higher levels? Even the programming language potentially, right? That makes programming harder, but think about it. I'm going to give you one example. This is basically the observation. Basically, the observation is that overwhelming majority of DRAM rows can be refreshed much less often without losing data. And this is real example from real data. For example, if you do not refresh rows every 64 milliseconds, but if you refresh every 128 milliseconds, only 30 rows lose data. Basically, only 30 rows go wrong. Not bad. You can fix that some way. If you refresh every 256 milliseconds, only 1,000 rows go bad. It says cells over here, but take that as rows because they're randomly distributed across the chip. Basically, you can cut the refresh rate by 4x, reduce the refreshes by 75% by producing unreliable rows, only 1,000 unreliable rows. That may be doable, right? That's the idea over here. Maybe the operating system can fix it. I don't know. So the question is, can we exploit this to reduce refresh operations at low cost? I already said this basically. Only 1,000 rows and 32 gigabyte DRAM we need to refresh every 64 milliseconds, but we refresh all rows every 64 milliseconds. So if you see a picture like this, then you should question. Say, okay, maybe I can do better. And the key idea that we did in a work that we published 10 years ago is to refresh weak rows. These are weak rows. Some rows are weak. They need to refresh more frequently. Some rows are strong. They need to refresh less frequently. Refresh only the weak rows more frequently and everything else less frequently. And that gives you a lot of performance improvement. I'm not going to go into the details of how to do this. You can actually, if you're interested, this paper is really easily accessible. You can read it. But basically, you need to identify the retention time of DRAM rows. You need to basically store this information somewhere. And there's a clever mechanism called Bloom filter that does it. How many people know about Bloom filters? Oh, no one? Okay, maybe I'll have to introduce it in a later lecture since we don't have time today, because it's something really important. Maybe you'll learn about it later. But basically, you have DRAM, you figure out this information and expose it to the memory controller. And you can do that with very low overhead using Bloom filters. Since we don't have time, unfortunately, I have backup slides. If you're interested, you can take a look, or earlier lectures in the past, or the lecture that I mentioned here. But we won't have time to talk about Bloom filters. And the memory controller refreshes rows in different bins at different rates. That's simple, basically. And let me give you the results, basically. If you do a simple idea like this, it sounds very simple, right? And I think it's very simple, actually. Hardware cost is low. Refresh reduction is almost 75%. You can actually extend the idea to reduce the refreshes by more than 90% too, but hardware cost increases. DRAM energy reduction is 16%. And when DRAM is idle, like now, for example, I can reduce the power by 20% here. And performance improvement also comes. Basically, it's an idea that improves performance as well as reduces energy. This is the sort of idea that we want going into the future, basically. We don't want performance with a lot of energy. We don't want lower energy with huge performance losses. We want something that improves performance as well as improves energy efficiency at the same time. Yeah, this sort of idea makes a big difference, basically, in general. And benefits actually increase as DRAM scales in density. You can watch this. But for example, in future DRAM, the benefits are much higher. The energy reduction is 50%. The performance improvement is almost 100%. Because future DRAM is a much bigger problem. These results that I show you over here is today's DRAM. But we always design for the future. 10 years down the road, what is the impact of an idea, right? 10 years down the road, the impact is much bigger. So the takeaway, again here, we broke the abstraction layers, right? We said, I'm refreshing something every 64 milliseconds. Should I really do that? What if I break the abstraction layer and say, look at the cells. These cells don't need to be refreshed that much. Actually, most of them don't need to be refreshed that much. So let me break the abstraction layers and understand what's underneath so that I can solve this problem. And this is the paper, if you're really interested. And there are further readings as well and detailed lectures on memory refresh. And if you want to learn about Bloom filters, we actually talk about Bloom filters in this lecture. But unfortunately, I don't have time for that right now. I can take a quick question on this. Any thoughts? Is there a way to fix the problem in a better way? Okay, one more. So exactly, that's another different thinking, basically. Today, we refresh the entire chip because the memory controller doesn't know which memory is allocated or not. And that's a very good, another question, right, basically. If memory is not allocated, why are we refreshing it today? It should not be done. The problem is today, it's this information, whether a piece of memory is allocated, is not communicated to the memory controller. Even though the operating system knows it, it doesn't communicate this information because there are no communication channels. But if it's communicated, you can fix that problem also. And there are actually papers that propose that. Yeah, it's this sort of critical thinking. Maybe there are other wastages that happen, right? Or maybe some parts of your program are actually, you don't care how much errors you get. And there are some parts of your program that are tolerant, actually. And if the errors you get by reducing the refresh rate is not a lot, maybe you reduce the refresh rate on those parts of your program data. That's another way of thinking, right? That way you're breaking the boundary between the hardware as well as the program that you're designing. Maybe programming language has actually ways of actually enabling this information. Okay, any other burning comment, question? Otherwise, we'll take a break. Okay, let's take a 10-minute break right now, and then we will start with lecture, I guess, 3B.